The third of our substances that we're going to have to explain the properties of are our covalent networks. There's only 3 you need to know about this year. There are more that exist, but there are only 3 that we focus on. Silica, which is sand and glass. You can restructure it so that it's not sand anymore, but it's glass. Graphite, which is pencil lead, so it's not really lead, it's graphite. And diamond, which I think is something we'll know what that is. The particles in covalent networks, and I think the video isn't going to show very well because there's a bit of reflection there, but the particles are always atoms. So here's a structure, here's a model of diamond. The particles are all carbon atoms. In silica, it's 1 silicon atom for every 2 oxygens, and it's a ratio. It's not a silicon dioxide molecule like you think of carbon dioxide. They alternate 2 oxygens for every 1 silicon in a network that looks really similar to diamond in a 3-dimensional lattice like this. The bonds between them are covalent because you'll notice that everything here is a non-metal. So non-metals have to share electrons, so the bonding or the forces between particles are covalent. The structure is called a 3D lattice, much like we've got for a covalent, for an ionic compound. Thank you. So we have a 3D lattice.
Should have said it for lunchtime.
This is going to be great on the video, isn't it? So it's a 3D lattice, much like ionic substances. And that's good for you to think about because that helps us explain those first, well, actually, all 3 of those properties there. It's much like an ionic compound in that way, but it's different because it's covalent bonds, and rather than its particles being ions, they are atoms. So there's a few little differences there. I've got a wee asterisk there and I say except graphite because of course it's NCEA. We're going to want to make sure we focus on or compare and contrast with the exception to the rule. In graphite, rather than every carbon having 1, 2, 3, 4 covalent bonds coming off it, has only 3. And it ends up being laid out in sheets like you can see across the top of the diamond there. And there's if we were using our models, there'd be a hole on every single carbon, which suggests that there is an electron that's not involved in bonding. Well, that, what we call delocalized electrons, that electron that doesn't sort of belong to anything, that valence electron, goes in between the sheets. So there's a sheet above and a sheet below this one here. So this is carbon atoms, each of them with 3 covalent bonds, and a delocalized electron. And they give them into the gaps between the sheets. So there'd be delocalized electrons here as well, and here. So I'm just showing a section of it. Those delocalized electrons give graphite some really unique properties. It's really hard to break the sheet because it's got covalent bonds and they're strong. They're not as strong as ionic, but they're pretty darn strong. So it's hard to break a sheet open. But because there's something that can conduct electricity between each sheet, delocalized electrons, delocalized means they don't belong to any atom. They can move, they can flow. So the delocalized electrons can allow for an electrical current to flow. They also give non-directional bonding. So there's no direction in the bonds between sheets at all. Unlike in diamond, where everything's a covalent bond, which is directional, there is no directional bonding between the sheets. That means they've got a really weak bond between each layer, and the layers will slide over each other very easily. Therefore, graphite is a really good lubricant because it's dry, so you can put it between things in machinery and it doesn't get wet, it doesn't cause any issues with the metal, and the sheets just slide over each other because of the delocalized electrons, the sheets having a very weak relationship or bond between them. So graphite's a really important exception to the rule that you're often asked to compare and contrast with diamond. So what they have in common is that they have carbon atoms. What they have in common is that those carbon atoms are bound to each other by covalent bonds. And you could even say strong covalent bonds because they are. What they have that is different is that diamond is our 3-dimensional lattice, like this, whereas graphite has not a 3D lattice, but sheets of carbon atoms bound together and delocalized electrons in between them. Graphite has got a very, very high melting and boiling point. It actually atomizes. When you break these bonds, they actually become carbon atoms. It is strong and brittle, and it's an electrical insulator. Contrast that, while graphite has a very high melting and boiling point still, because to break those covalent bonds is hard, it is not strong or brittle. It is actually slippery. The sheets can slide over each other. So it's a good lubricant, and it is an electrical conductor because the delocalized electrons in the middle can flow. So if I put a positive charge here, they'll be attracted to it and create a flow of electricity. Negative charge here, push away, creating an electrical flow. Are there any questions before I turn this off? Cool.